Right, I'll just go full screen as well. Okay, at some stage we'll need to come out of this to use the whiteboard. So with Basic Phys Chem 2, we're going to continue with this series and look at solutions of macromolecules and deal with concentration and concentration measurement. Looking forward to the practical demonstrations which will follow in due course, and look at the importance of ionic strengths of molecules in solution, or ionic strength of solutions caused by the presence of ions, how we calculate that, and some examples, and why it's important in terms of solutions of macromolecules. And then we'll look at the volumes of macromolecules. Again, that depends on the relations of the molecules with the watery environment which they find themselves in solution, and how we represent volumes, and in terms of what's called specific volumes. And again, this will point towards the practical demonstration that we'll be doing shortly on this. Right, so solutions. I can just go to full screen. That's good. Right, so macromolecules often occur in a watery type of environment. So it's important to understand the relations between macromolecules and water, and solubility and concentration. And the very first thing we have to do is to just look at the properties of the water itself. And the water has structure, and though at first hand it doesn't seem that way, but water has structure even in liquid form. So water is a polar molecule, so it has a net negative at the oxygen, and net positives with the hydrogen. So the electron cloud is not uniformly distributed throughout the water molecule. There is a higher negativity at the oxygen compared to the hydrogens. The water molecule isn't ionized, but is polar because of the uneven distribution of the electron cloud or charge. And that means that water itself can form hydrogen bonds between the electronegative and electropositive parts. This is a dynamic structure, so it doesn't form a rigid structure, not in the liquid state. Anyway, in the solid state, in ice, this is different. But in liquid water, there is local dynamic structure where hydrogen bonds are being formed, broken, reformed, broken, reformed. But over, like average over time, then one can say that there is structure within the liquid water situation. So if we're going to dissolve molecules in this, including large macromolecules, proteins, polysaccharides, nucleic acids, glycoproteins, or what ever, then in order for these molecules, these macromolecules to dissolve, again, the free energy change has to be negative. So delta G m, where little m represents the free energy change of mixing. Again, it's governed by this equation here, which comes from the second law of thermodynamics. Delta G m equals the change in the enthalpy, or heat energy at constant pressure, of mixing, minus the temperature times the change in the entropy of mixing, or the degree of randomness. That's what the entropy is. So if the system becomes more random, then there'll be an increase in the entropy. So delta S increases. And since this is a negative here, minus T delta S, that will be energetically favorable. That's what happens, when we dissolve a macromolecule. It disrupts the hydrogen bond structure within water, which is favorable, at least in terms of the entropy change, because it becomes more random. However, because we're breaking bonds, that leads to a positive change in the enthalpy or heat energy, which is not favorable. So if a macromolecule is going to dissolve in water, then this term has to be more negative than this is positive for the free energy change to be negative, which is the condition for the reaction to occur. So solubility is this playoff between polar or hydrophilic and hydrophobic interactions. The more hydrophilic groups there are, the more disruption of the water structure, and the more likely the molecule is going to dissolve. So this interplay between polar or hydrophilic and non-polar or hydrophobic interactions, and that explains why, for example, polysaccharides, polymers of sugar residues, some polysaccharides like arginates are readily soluble, whereas other polysaccharides like cellulose are insoluble, and other polysaccharides like the galactomannan will dissolve, but with some degree of difficulty. It's all to do with the playoff between polar and non-polar or hydrophobic interactions. Right, so let's assume we've managed to dissolve our protein or polysaccharide or nucleic acid into solution of water, or it could be water in the presence of salt ions. There could be salt ions present. It could be buffer ions. It could be a controlled environment with a controlled pH. Let's just assume that we can dissolve our macromolecules into this aqueous, watery situation. Then how do we represent the concentration of material that's dissolved? Well, there's two main ways that we concern ourselves with here. One is the weight or mass concentration, symbol, well, usually it's symbol capital C, or that can vary. That's defined as the mass of solute dissolved in unit volume of solution. And the SI units are kilograms per meter cubed, but again, when we're dealing with molecules and macromolecules, this is rather an inconvenient set of units. So we tend to use the CGS, centimeter gram second system, and the units there are grams per centimeter cubed or grams per mil. A mil is the same as a centimeter cubed. That's, if you like, the common concentration units, the mass of solid dissolved in unit volume of solution. There's also the molar concentration, which is often given the symbol lowercase c, and that's a measure of the numbers of moles dissolved in per unit volume of solution. And 1 mole is 6.022 times 10 to the power 23 molecules, which is the Avogadro's number. So the molar concentration relates directly to the numbers of molecules that are dissolved in solution, whereas the mass concentration relates directly to the masses of a molecule, a macromolecule, dissolved in unit volume of solution. So numbers and masses. And the numbers, it's not straight number concentration, but it's number concentration related by the Avogadro number. And the molar concentration is related to the weight concentration. You simply divide the weight concentration by the molar mass in the appropriate units. And if we're dealing with CGS units, that would be in gram per mil, and the molar mass would be in grams per mole, which is the same numerically as a Dalton unit. So if we divide grams per mil by grams per mole, we end up with mole per mil as the CGS unit, if you like, of molar concentration. The SI unit, the molar concentration, is moles per meter cubed. And we also represent molar concentrations as molarity in terms of moles per liter. And moles per liter is neither a CGS nor an SI unit. So, beware of the different ways of representing the different units for molar concentration. Right, so that's how. There's other forms as well, such as molality and mole fraction, but we won't cover that in this course. If you do the MRes in biomolecular technology, then sure, we will cover it in detail, but not with this course here. So let's say we have our molecules dissolved in solution. How do we measure the concentration? Because concentration is a very important parameter, as we'll see later on in the course. Well, the simplest way in concept anyway to measure concentration is dry weight measurement. That means you just evaporate off. First of all, you measure the volume of your solution, then evaporate off the water, and then you measure the amount of solid materials left behind. That, in principle, could give you the dry weight concentration. Of course, you wouldn't dissolve, you wouldn't evaporate all your material because you'd lose what you wanted to look at. You just take an aliquot or proportion of that to assay for the concentration. So that to be accurate, you need relatively large amounts of material, which are not usually recoverable. And also you have the complication of, if it's not just dissolved in water, but dissolved in a salt solution or containing buffer salts, then they would need to be removed by dialysis before drying, or instead you perform a suitable control which just has the buffer salts in solution and not your macromolecule. So there are complications if you try this method. If it's a protein, you can assay for the concentration by measuring the nitrogen content. This is called a Kjeldahl analysis, but this assumes that the nitrogen content is uniform across the range of proteins, and that's not always the case, particularly when you have larger amounts of amino acids which contain nitrogen containing side groups. So proteins only needs large amounts of material, or relatively, not recoverable, and there can be complications depending on the amino acid composition. The most popular way of measuring concentrations for proteins, and we'll see that in the demonstrations, is using a spectrophotometer. Now, have all three of you, have you used a spectrophotometer before?
No, I've heard of it, but not used it before.
Hands up.
Not quite.
And Latika?
Yes, I have used.
Okay, so we'll when you come over to the NCMH in a fortnight's time, we'll show you how the spectrophotometer works. It's used for several reasons. You can look at enzyme kinetics. You can assay from the spectra of a solution in terms of composition, and we can use a spectrophotometer to determine concentration. And that's because proteins absorb usually quite strongly in the ultraviolet, in what's called the near UV, which is around 280 nanometers. And this is because of the presence of, well, you tell me, folks, what amino acids in a protein molecule absorb quite strongly around 280 nanometers? Anyone? Well, it's usually the ones with aromatic side chains coming off. Tyrosine and tryptophan have UV absorption maxima around 278, 280 nanometers. There's also phenylalanine, but that absorbs at a slightly lower wavelength, around 256 nanometers. But generally around 280 nanometers, you get a reasonable absorption, depending on the amino acid sequence and the proportions of tyrosine and tryptophan in the protein, and also on the concentration of the solution. So the more concentrated the solution is, the more tyrosine, tryptophans you will have, hence the higher the absorption. It depends on the composition and on the concentration in terms of the strength of the absorbance. Nucleic acids absorb strongly around 256 nanometers, and that's because the nucleotide bases absorb around there. So if we're using a spectrophotometer for looking at proteins, normally we go 280 nanometers, and for nucleic acids around 256 nanometers. And again, we'll see this when we do the demonstration in 2 weeks' time. But essentially, you put your protein solution in a what's called a cuvette. This is made of quartz or something that's non-absorbing in the near UV, or special non-absorbing plastics, and the solution goes in there, and then that's placed inside a spectrophotometer. And in the spectrophotometer, you have a monochromatic light source. This is a light source where you have what's called a monochromator, and that is, the wavelength is set by the user. So if we're measuring concentrations of protein solutions, we would set the wavelength normally to 280 nanometers, and you have an instant beam of intensity I0, and if you've got tryptophans, tyrosines and things there, that will absorb the UV radiation, with the result that the intensity which comes out of the other side of the cuvette after it's been through the protein solution will have a lower intensity because of the absorption of some of the incident light. The path lengths of these cuvettes can vary, but a typical one is about 1 centimeter in length. You can use much shorter ones if you have a very concentrated solution. And the intensity of the light after passing through here is collected by a detector in the spectrophotometer using a photomultiplier, and then sent off to a digital readout or computer. And what the spectrophotometer does is it compares the intensity of the transmitted beam with that of the incident beam. And the absorbance is measured, which is defined as log 10 of the ratio of the instant intensity divided by the transmitted intensity. So the absorption, after you've measured it, is proportional to the concentration. Well, it is within a certain absorption range where this equation applies, and this is known as the Lambert Law, or the Beer-Lambert equation, which says the absorption is proportional to the concentration. The absorption equals this parameter here, this epsilon subscript lambda, which is called the extinction coefficient, and that will depend on the wavelength. Okay, and this particular value will depend on the wavelength and also on the particular protein or nucleic acid. So the more, for example, proteins, the more tryptophans and tyrosine amino acids you have, then the greater will be the extinction coefficient. Polysaccharides, by the way, have no tryptophans and tyrosines, so they will have an extinction coefficient of 0. And hence, we generally find that in the near ultraviolet, that means around 280 nanometers, the absorbance of polysaccharide solutions is also 0. That's why we can't really use spectrophotometers for looking at the concentrations of polysaccharides. They do absorb at much lower wavelengths, around 200 nanometers, but there are other complications down there from interference from salt ions and other things which could also contribute to the absorption down at those wavelengths. But around 280 nanometers, polysaccharides don't absorb, so that's why we can't really use the spectrophotometer, at least at those wavelengths. Okay, so for example, of albumin, a protein, this has an extinction coefficient at 280 nanometers of 660 mils per gram per centimeter to the -1. L is the path length of the cell, so the longer the path length, the greater the absorption, and C is the concentration, the weight concentration. So if you measure the absorption, you know the extinction coefficient, the path length, you can measure the concentration with a spectrophotometer, provided that the absorbance is less than 1.4. This equation only applies up to a value of about 1.4, depending on how accurate and how, I suppose, expensive your spectrophotometer is. But generally speaking, once you go above 1.4, then this law tends to fail. So it's applicable generally only up to absorbance values of 1.4. So if you put your protein solution in a cuvette and you measure the absorbance and you get a reading of greater than 1.4, what should you do? Should you abandon the measurement and look for some other technique, or is there something else we can do? Okay, what we can do is we can take an aliquot, a sample of your solution, and dilute it by 10 times, 11 times, or whatever, and then measure, accurately record what the dilution is, how much you diluted your solution by, your aliquot by, measure the absorbance of that aliquot, and so long as it's between 0 and 1.4, you can record the absorbance and then multiply by what the dilution factor is, and then you can get your concentration. So if you find your value is above 1.5, don't panic, just go back and do a dilution of your stock solution, take it aliquot and dilute it, and then if it's still above 1.4, dilute again, and then just get the absorbance into a range which you can measure, and then make a record of the dilution factor, which you then correct for at the end. And we can also use the what's called a molar extinction coefficient, which relates to the molar concentration. The molar extinction coefficient and standard extinction coefficient are related by the molecular weight. There's a molecular weight correction factor you apply to switch from one to the other. And this has units mils per mole per centimeter to the -1, as opposed to mils per gram per centimeter to the -1. Okay, well, we'll have practice of doing that when we do the demonstration in 2 weeks' time. So I just mentioned it, but why? What reason did I say that this method is not generally suitable for polysaccharide solutions? You're measuring the concentration of a polysaccharide solution. Why would you normally not use a spectrophotometer? Because around 280 nanometers, polysaccharides, they don't absorb UV radiation. So there's no point in using this technique if your macromolecule doesn't absorb in the what we call the usable UV or visible range. And similarly, if your protein is colored like myoglobin or hemoglobin or cytochrome C, then we could also use the spectrophotometer in the visible region to calculate concentrations in addition to 280 nanometers.
But
Okay.
can you just adjust the the wavelength of the light source to where the polysaccharides can absorb?
That's absolutely correct. So you do that for nucleic acids down to 256 nanometers, but for polysaccharides you would need to go right down in wavelength to around 200 nanometers, and then you may run into problems of the presence of salt ions and other material in the solution, which could absorb. So in principle that's correct, but in practice it's not easy for polysaccharides. You can do that with proteins as well. You could go down and basically recording the absorbance due to the peptide bond as opposed to the glycosidic bond with polysaccharides. But it is tricky. And generally speaking, if your molecule doesn't absorb in the near UV, that is 280 nanometers or 256 nanometers, then it's actually much easier to switch to a different type of measurement based on what's called refractometers, not spectrophotometers. And again, when we do the concentration demo in 2 weeks' time, you'll see how we operate refractometers. It's very similar in principle to spectrophotometers for measuring concentration, but instead of measuring the absorption of light in the UV or whatever, we're measuring the
refraction rate.
Yeah, refraction, that's right, the bending of light. And the way a solution or material, well, a material will bend light depending on its composition. So, water will bend light, glass will bend light even more because of its different composition. And solutions and molecules will also deviate path of a beam of light depending on the concentration. So the more concentrated a solution is, the more the bending of light. And it also depends on the composition of the material, if it's a protein or polysaccharide or nucleic acid, and also depending on if it's a protein amino acid composition. This will affect the bending. So we have a very similar equation to the Lambert-Beer equation for absorption, and this is as follows: it's N minus N0 equals R times C, where C is the concentration again, the weight concentration. N is the refractive index of the solution. N0 is the refractive index of the solvent, so it could be water, or if it's a buffered solution, it could be a phosphate chloride buffered solution, or it could have some small electrolyte in there, like a sodium chloride solution, so that will also contribute. But whatever, N is the refractive index of a solution, and N0 is the refractive index of the solvent. And usually it's an aqueous solvent in which your protein or polysaccharide or nucleic acid is dissolving. So N minus N0 equals concentration times this, which is the R is the specific refractive increment, which is sometimes given this symbol here, dN dC. That's the refractive increment, the change in refractive index with concentration, dN dC, which is often given the symbol R, or dN dC. So the amount of bending, or N minus N0 of a solution compared to the reference solvent, depends on the composition and depends on the concentration. For proteins, generally R is about 0.19 mils per gram. For polysaccharides, it's about 0.15 mils per gram. If it's a glycoprotein, which contains a mix of protein and carbohydrate combined together, like ovalbumin, antibodies, or mucin glycoproteins, for example, then it'll depend on the composition, the relative composition of protein to polysaccharide. So what values do you think glycoproteins would have? What would be the range of values that glycoproteins would have in terms of the refractive increment? So proteins are this, polysaccharides are this. So what range of values do you think glycoproteins would have?
The value will be between these two values.
Exactly. So it depends on the degree of glycosylation of the molecule. So the more glycosylated it is, then the more like a polysaccharide. So for example, a mucin glycoprotein, which is 80% sugar and 20% protein on average, that would have a refractive increment of 0.6, something near that of polysaccharides. Whereas ovalbumin, or an antibody molecule with a relatively small amount of glycosylation, then it would be between 0.8 and 0.9, nearer to the protein. It depends on the degree of glycosylation. Anyway, we'll see that when we come here in 2 weeks' time. You'll be able to compare how we use a spectrophotometer with a refractometer. And it's actually in the lab next door. If I could stretch the camera, I'd take it with me into the lab, but unfortunately the camera is not a portable camera, and I might do some damage if I tried that. So if you can bear with us, and we'll show you the equipment and show you an example of the determination of a concentration when you come in, I think in a fortnight's time. Okay, so spectrophotometers and refractometers for measuring concentrations of your material in solution, and that's probably the most popular way and most accurate way of measuring concentrations, providing you know refractometry what the refractive increment is, or if you're using spectrophotometer, you know what the extinction coefficient is. And when you come here in 2 weeks' time, we'll show you the operation of a program which is used to measure volumes of macromolecules, how that program will also work out the extinction coefficient of a protein or glycoprotein, depending on the composition of the molecules. It's a program called Perkins, which we'll see operate. Right, there's Oh, yeah, okay, we might go beyond 12 o'clock here, folks. We might go on till about 10 past 12. Is that okay with you guys?
Yeah, it's fine
Yeah.
for me.
Okay, so we just got to cover ionic strength, and then we've just got to cover volumes. So the next concentration related parameter is ionic strength, and this refers to the strength or concentration of ions in solution. So it's specifically to do with ions rather than the concentrations of protein or polysaccharide or whatever. And the ionic strength is defined by this formula here. So it's half times the sum of the concentration of an ion. This is the molar concentration in moles per liter or moles per mil, whatever, as long as you're consistent with the unit you use. So it's the concentration of an ion times the square of the valency of that ion. So if it's sodium, it's 1. If it's magnesium, it will be 2. And it's the square of that valency. And so you do that for one ion, and you do that for the other ions that are present in the solution, and add them all up. And then multiply all that by a half, and that gives you the ionic strength. So Hang Zhao and Zizang, is that more or less what you were taught before?
Yeah.
Yeah, quite the same.
Geochemistry?
Mhm.
Okay, Lathika? You met this equation before? Yeah. Okay, well, just to show you how it operates, and this might be a good revision for Zezang and Hang Zhao. We're now going to calculate the ionic strength of these two solutions. And for that, I'm going to temporarily come out of the screen share, and you should see me now. Yeah, we're probably equal size. You probably on your screen you've got you probably see yourself in a corner, and you've got a picture of the rest of us on the screen. Is that correct? Right. So you need to probably maximize me. So in order to see this, you'll need to maximize me if you can. There's a way of doing that. Right. Can you see me?
Yeah.
Yes.
Am I coming out in full, or am I coming out still as a small square?
It's large enough.
Yeah, it's large.
Okay, can you see that?
Yeah.
Yes.
Right. This is the big test now, folks. Let's juxtaposition the chair and things. So there's two. Right, I have to bend down here. Can you see the top of the? Let's just position this down a bit. How's that?
Yeah, it's good.
Yeah.
Right, so we've got 2 0.1 molar NaCl and 0.1 molar MgCl2. So let's do this one first. 0.1 molar. You want to see that?
It's a bit shiny, but
Let me turn the light off. And close this. Okay, is that any better?
Yeah, much better.
Right, so can you see that?
Mm.
Yes,
What does that say?
0.1 mole.
Right, so the ionic strength, I, well, let's take NaCl first of all. NaCl,
That's 0.1, I think.
associates completely to give one molecule of NaCl gives 1 ion of sodium and 1 ion of chloride, correct? So 0.1 molar of NaCl gives 0.1 molar of sodium ions plus 0.1 molar of chloride ions. Is that okay?
Yeah.
So the ionic strength, I, equals half times the sum of
That's
molar
not,
concentration times the valency squared. So let's take the first ion, which is sodium. So I equals, we'll put a half out here. So what's the concentration of the sodium ions?
0.1.
0.1 times, and what's the
1.
valency or charge?
1.
1. That's 1 squared. That's the sodium ion. And the chloride ion?
0.1 and minus 1.
0.1 and then minus 1 squared. So what's minus 1 squared?
1.
1. So what's the ionic strength then?
0.1.
0.1.
0.1. So it's half times 0.2, which is 0.1. So you may think from that, well, that was a waste of time because it's just the same, 0.1 molar NaCl, the ionic strength is the same. So why have we wasted our time doing that? Well, in a way, this is coincidence. This happens to be the same for what we call a univalent electrolyte, where you have the same one positive charge on one ion and one negative charge on the other ion. Just happens to come out the same. Let's look now and see what happens for magnesium chloride. Let's just now highlight. Let's just rub all this out again.
That's 0.3, I think.
Yes. Let's just confirm that. So we've got this time MgCl2 gives Mg2 plus how many ions of chloride?
0.2 or 2.
2 ions of chloride whose valency is just a single minus. So 0.1 molar MgCl2 gives 0.1 molar magnesium ions. And how many molar of chloride ions?
0.2.
0.2. Okay. So this time, I equals a half. Well, let's write down the equation again properly. Di squared summed over all the ions equals half. Take the first ion. So what's the concentration of magnesium ions?
0.1.
0.1.
0.1 times the valency,
2.
2.
2 squared. And then we take the next ion, which is chloride. So how many moles?
0.2.
0.2 times valency.
-1.
So that equals half times, that all adds up to
0.6.
0.6.
6. Right, 0.3 molar. That's not the same as that, so that shows you the ionic strength isn't always the same as the dissolved molar concentration. So that's how you work out the ionic strength. So is that all clear?
Yes.
That hangs out and Latika? Fabulous. And where this is relevant is from, well, I'll start off with an environmental science example, then we'll look at its importance in terms of the properties of proteins, polysaccharides, and other solutions of macromolecules. Let's switch back to the presentation again. I'll just unhighlight me, if I can. Exit spotlight. Right, so I'm no longer highlighted. That's very disappointing. So if I go to share screen again, and we go back to the presentation. Okay, so that's 0.1 molar, and that's 0.3 moles. And okay, so to convert that to moles per mil, what's 0.1 moles per liter in moles per mil?
100. Is it?
So a mil is that a less volume or greater volume than a liter?
Less.
Less. So you need to divide by
1,000.
1,000.
1,000. Okay, that converts moles per liter to moles per mil. So it'll be 0.1 times 10 to the minus 3, or 1 times 10 to the minus 4 moles per liter, and that would be 0.3 times 10 to the minus 3 moles per mil, or 4 times 10 to the minus 4 moles per mil. Yeah, so remember that when converting. Let's go back to full screen again. Right, so the ionic strength of seawater is very high, actually. That's high. 0.7 molar is very concentrated, or very ionic in terms of the ionic concentration. And in seawater, the main contributors are sodium and chloride, of course, but also magnesium and sulfate. Very different from surface water, groundwater, fresh water, which is much lower. Although you can get significant variations, especially if there's been some local mining operations or whatever, which can increase significantly the ionic strength, and that can have an impact on the local ecology, life forms and things that are in the environment. So ionic strength is a very important environmental parameter. And again, this is all linked to not just climate change, but also to as climate changes lose water, the sea becomes more concentrated, and that can have an impact, but also on the effects of pollutants on the ionic environment in which living organisms in particular can find themselves in. That affects the ecosystem. That's a very important parameter. But also in terms of the macromolecular chemistry, protein, polysaccharide, nucleic acid chemistry, the properties of molecules in solution are affected by the ionic environment, especially if you're dealing with charged molecules like proteins, many polysaccharides and nucleic acids. You put proteins which can have a high charge, high valency, polysaccharides, nucleic acids, they've got loads of negative charges because they've got all these phosphate groups on them. If they're just in pure water, then what do negatives do? Lots of negative charges. Okay, I'm a very negative nucleic acid. I'm coming near another negative nucleic acid. What happens?
Repel.
They repel. Okay, you get strong repulsive forces. I mean, many macromolecules in nature are negatively charged. They have high charges. They're called what's called polyelectrolytes, polyanions. That's high negative charges, but you can also get polycationic materials as well. These have high positive charges. Histones, a protein which is used to condense DNA, has a high positive charge. But these molecules will repel each other, and that can lead to all sorts of properties. Can be very unfavorable properties in solution if not controlled. But if your protein or nucleic acid or whatever is sitting in a solution which has 0.1 molar sodium chloride or something in there, then what the salt ions usually do is to shield the charges. They shield the charges on the proteins and the nucleic acids and the polysaccharides from each other, so that decreases or minimizes any repulsive interactions that are taking place. It reduces what's called the non-ideality of solutions of macromolecules, and this is very important, as we will see next time when we do, well, not next time, when we do Physical Chemistry 3, you'll see how important this control of the so-called non-ideal properties of solutions are concerned. So not only is ionic strength a very important parameter directly in the environment, in the control of eco-environments, ecosystems and things, it also has a strong impact in terms of the conformation and behaviors of proteins, polysaccharides, nucleic acids, the molecules of life in solution. So it's a hugely important parameter, ionic strength, when dealing with charged macromolecules. Okay, that's why I've dwelled on about ionic strength. Hopefully you'll forgive me for that, but it's a very important concept. The final concept, and again, this will link with the demonstration that we do in a fortnight's time, and that's on the volumes of molecules. And sometimes it's more convenient to deal with specific volumes, and specific volumes means volume per unit mass. It's like with specific heat. Remember that from school or whatever? I did a degree in physics actually, so I had to do it in my degree as well. We see specific heats. It means heat capacity per unit mass. In the same way, specific volumes refer to volume per unit mass, and the unit we usually use is mils per gram. So in a sense, it's the sort of reciprocal of density, because density is mass per unit volume. Specific volume is volume per unit mass. And the reason why it's useful is, or one of the reasons, is it enables us to represent the water relations of macromolecules. Macromolecules can swell. That means the volume, effective volume, can increase because of the interactions with the water environment in which many of them will experience, especially when they're in solution. So a molecule, a protein or polysaccharide or whatever, will tend to have a larger volume in solution compared to the dry state because of its interaction with water through dynamic hydrogen bonding. Again, it's dynamic, water molecules binding, releasing and things. However, on a time average basis, we have this what's called hydration, which represents the water associated with the molecule on a dynamic basis. Also, you can get water which is trapped in the interstices. I say water, really I should use the term aqueous solvent because it includes ions as well that may be present in the aqueous solution. So the hydration or solvation or swelling of the molecule is a dynamic process which has a time averaged effect. So the volume of a protein or whatever is larger because of these hydration effects in solution. So on this diagram, the blue, maybe I should have used red actually and blue for water, but blue represents the anhydrous molecule and red represents the associated solvent, which is chemically bound or trapped, so bound in a dynamic way. And there's two useful specific volumes here. The first is the partial specific volume. Partial you could think of in terms of representing the dry part. So it's simple little v with a bar across the top, and the partial specific volume is the volume of the anhydrous molecule divided by the anhydrous mass. So mils per gram. The swollen specific volume, symbol little v with a subscript s, is defined as the volume of the hydrated molecule, because this water association, divided by the anhydrous mass. Not the hydrated mass, but the anhydrous mass. So this is the swollen specific volume. The volume of the hydrated molecule divided by the anhydrous mass. And how much a molecule swells depends on the nature of the molecule and its composition. And we generally find that sugars, polysaccharides, or molecules with lots of sugar on tend to have higher swelling, higher swollen specific volumes compared to protein molecules. And that's why polysaccharides and mucins and all these others that are often referred to as hydrogels. Polysaccharides are often used in, for example, nappy liners, or used in cat litters if you've got a pet cat, and especially if it's a young cat and can't let it outside, and we have these little litters where they can go to the loo. These molecules can absorb water to a high extent. So the swollen volume, the swollen specific volume, is greater than or equal to the partial specific volume, which refers to the dry particle. And how much bigger it is depends on the type of molecule. So for a protein, the partial specific volume is about 0.73 mils per gram. Again, it'll depend on the amino acid sequence, amino acid composition, and when we come to do the demonstrations in 2 weeks' time, we'll be measuring the partial specific volume on a computer program, which is designed to work out it from the amino acid composition. And then the swelling due to hydration, the VS will be a bit higher. So it depends on the composition, but it's usually of the order of 1 mils per gram. For a polysaccharide, V bar is 0.6 mil per gram, so it's a bit more denser. Don't forget, specific volume is the reciprocal of density, so 0.6 mil per gram. And it's not shown here, but the VS is usually much larger than 1 mil per gram. So the VS for polysaccharides is usually much larger than a mil per gram. And then for glycoproteins, again, it depends on the degree of glycosylation. So the very heavily glycosylated glycoproteins like mucins will have very high values for the swollen specific volume. All right, guys, so that is the end of this presentation. Again, I don't want to say any more now until we've had the demonstration in 2 weeks' time. So we dealt with, in effect, today, 2 water-related parameters. One is the concentration of molecules and the concentration of ions. So that makes 3, if you like, the ionic strength. And also in terms of the effect on the volumes of macromolecules, the volumes of proteins, polysaccharides, and how we represent that in terms of these specific volumes. And both, well, in fact, all of the concentration, the ionic strength, and the volumes of the molecules all affect what we call the non-ideality properties of macromolecules in solution, a topic which we are going to discuss next time. And with that, I'll just come out of that Okay, can you all see me again?
Yes.
Yes.